Welcome to Unit 10. In Unit 10, our goal is to explore another statistical technique that can be very useful for analyzing categorical data or, more pointedly, count data. And this statistical technique is called goodness of fit test and contingency analysis. Our target is to isolate situations when goodness of fit test will be appropriate and when contingency analysis will also be appropriate to answer business questions that can help support informed decision making processes. To get started, let us consider a motivating example for first goodness of fit test. So here is a motivating example or scenario that a goodness of fit test will be very appropriate for. Remember, part of learning statistics is being able to analyze situations and being able to match such situations with the appropriate statistical technique to use. In this example, we're told that employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed in the table below. So for Monday, we have 15, 12 on Tuesday, 9, 9 on Thursday, and 15 on Friday for this emphasis random sample of 60 managers. All right, so that brings up a question, and that is a research question here. For the whole population of employees, not the sample, the general population, do the days for the highest number of absences occur with equal frequencies during a 5-day work week? So our interest here is to see if the pattern we see in the sample is reflective of what's going on in the entire population. And we want to see if the evidence contained in this sample data points to that or otherwise. And our goal is to conduct that test for this claim at a 5% significance level. How do I answer this research question? Well, our interest is to check if this distribution in this sample is reflective or if it fits what we assume is going on in the population. In particular, our particular hypothesis here is focused on, do the days for the highest number of absences occur with equal frequencies during a 5-day work week? So our interest is, if we're looking at 60 days, if the absences occur with equal frequencies across Monday to Friday, what do you think? What is the average number of absences we should observe each day? What is the expected number of absences that we should expect each day if the claim that the highest number of absences occur with equal frequencies during each of the 5-day work week? What do you think? 60 divided by 5? I agree. That would be what? 12, 12, 12, 12, 12. But do we have exactly 12 here? Of course, there will be sampling error from one week to another. So does this sample data show a great departure from the expectation of 12 absences per day? Is that departure something due to chance and negligible? Or is it something that presents a significant amount of departure from what is expected that we would reject the null hypothesis? In situations like this, a chi-square goodness of fit test will be very appropriate. So, how do we answer this research question? By using the chi-square goodness of fit test. So let's see what that looks like. So chi-square, in Greek, this is written as chi-squared goodness of fit test, which is appropriate because we are interested in seeing if the data, the information contained in the sample data, fits with the claim for the entire population. What are the sequence of steps to follow? 1. We'll formulate the null and alternative hypothesis. 2. We'll specify the level of significance of the test. Then we'll take a random sample of data, which we have already been given, and we'll compute appropriate sample statistics and a test statistic for us to be able to reach a conclusion as to whether the sample data fits the hypothesized statement about the entire population, and then we'll draw a final conclusion. So back to this question, our interest is, let us take on each of the steps. So to begin with, we want to look at the null and the alternative hypothesis. In this case, the null hypothesis will indicate that the absent days occur with equal frequencies. In other words, it's the hypothesis of no difference. And that means that they fit a uniform distribution. A uniform distribution in the sense that for each of the 60 managers, if the highest number of absences occur with equal frequencies during the 5-day week, then you should have 60 divided by 5, which is 12 absences per day. In other words, they occur uniformly or with equal frequencies. On the other hand, we would have the alternative, which is that the absent days occur with unequal frequencies rather. Of course, we would like to go on to step 2, where we would like to specify the level of significance. If that is not specified in a given question, we assume that it is 5% or 0.05. So we specify level of significance as alpha, which is equal to 0.05 or 5%. Then we proceed to the next step, which is the model check. Before we jump into, that was an error there. Before we jump into this analysis, we would like to look at the model check or the underlying assumptions. So we shouldn't have an over here. That was an error there. So before we jump into the calculations, we want to look at the model assumptions. One is independence, and that is that each case that contributes to a count to the table must be independent of each other. No manager must be related to another, and that would guarantee independence of the sampled units. Then you have sample size and distribution. Each particular scenario must have at least 5 expected cases. Well, in this case, since we have 60 managers, based on the assumption that the null hypothesis is true, we'll be dividing that 60 absences by 5 days, in which case you have 12 expected absences under the assumption that the null hypothesis is true. So take note that the expected frequency is obtained by assuming that the null hypothesis is true and carrying on calculations in order to obtain the expected value. You see, failure to check the conditions may usually affect the test error rates. Recall that we talked about different types of errors associated with hypothesis testing in statistics, namely type 1 error and type 2 error. When expected cell frequencies drop below 5, then the test statistic we will get, which is the chi-squared value, tends to be inflated and may overstate the true probability of a type 1 error beyond the significance level of 0.05 or whatever significance level we're using. So as a rule, if the null hypothesis is not rejected, you do not need to worry when the expected cell frequencies drop below 5. This is an exception stated here. All right, back to the question at hand. We would like to go to the next step, which is to look at the data we've collected from the random sample and to compute appropriate statistics and the test statistics. What are those? Let us look at them. Well, for the mechanics step, we would like to note that we have 60 managers in the sample. And so what is going to be the degree of freedom for the chi-square distribution that we're going to use to carry on this test. The degree of freedom is k minus 1. In this context, k is the number of what? Categories. And there are 5 different days in this case. So 5 minus 1, that is equal to 4. That is how we obtained the degree of freedom. So that matches what we get from StatCrunch. I'll show you that in a little bit. Then, what is the chi-square value? Let us compute that manually first. Then we'll later go to StatCrunch to also do that. Well, we have the observed values for Monday, Tuesday, Wednesday, Thursday, and Friday. This was also observed in the sample data for absences. Then what was expected? Well, if we have 60 days divided by 5 different days, for each of the days, under the assumption that the null hypothesis is true, that absences occur with equal frequencies, then 60 divided by 5 will give 12 equal absences for each day. With that said, we have our observed values, which I'll tag OIs, and our expected values. The I there represents 1, 2, 3, 4, 5. Day 1, day 2, day 3, day 4, day 5, Monday to Friday. So, in order to get the chi-square test statistic, so I'd like to emphasize that this is the test statistic. We use the formula chi-squared equals the sum of the expected what? Of the sum of each of the observed values minus the expected values squared and then divided by each of the expected values. What does that mean? In other words, it means if we started with looking at the formula OI minus EI, that means I'll take each observed minus the expected. So for instance, this will be 15 minus 12, which is 3. The next one is 12 minus 12, which is 0. 9 minus 12, which is negative 3. 9 minus 12, which is negative 3. 15 minus 12, which is also what? 3. Then the next step will be to square the answers because the formula says we should square the answers. So I'm going to push 3 forward. I'm going to square it. I have 9. 0 squared, I have 0. Negative 3 squared, I have 9. Negative 3 squared, I have another 9. And then 3 squared, I have another 9. Now, the next step would be to take that squared value and divide it by the respective expected value. In other words, the 9 we just got divided by the expected value, which is 12 for each of the rows. So similarly, I have 0 divided by 12, 9 divided by 12, 9 divided by 12, 9 divided by 12. Then my chi-square test statistic is the sum of all of these guys. Where are all of these guys? They are right here in the last column. And so I'm going to sum over them. So that will be 9 over 12 plus 9 over 12 plus 9 over 12 plus 9 over 12. That will be over 12, 36 over 12, which is equal to 3. We can get this from StatCrunch. Then the final step will be to get the corresponding value using the chi-square distribution. So I've pulled up what? The chi-square calculator in StatCrunch. I have supplied the degree of freedom. I've also supplied the chi-square value here. And I can get this is my 3 here. What is the probability that is equal to that chi-square test statistic value or even more extreme? And I have the probability, which StatCrunch can also provide. So now that we have found we've uncovered what the degree of freedom is, the chi-square test statistic value, and the p-value, let us go into StatCrunch and see how to implement the chi-square goodness of fit in StatCrunch. So I am going to minimize this. There we go. And let's go to StatCrunch. Oh, excuse me. Let's go back. And let me pull StatCrunch from here. Good. All right, I had this up earlier. So let's go back to the question. If we go back to the question, I have the number of absences, which I have tagged absences. So I have 15, 12, 9, 9, and 15. 15, 12, 9, 9, and 15 in one column. To implement the goodness of fit test, I'll go to statistics, scroll to goodness of fit, go to chi-square test, and my interest is what was observed in my sample data. All values were saved under the column absences. Absences, absences. Then, in this case, what is my research question? I anticipate that they occur with equal frequencies. So I'm going to click on all cells in equal proportion. By clicking on this, StatCrunch will take the sum of absences, which is 60 absences, and divide by what? How many groups? 5. And so it will automate the process of saying 60 divided by 5 to get what? The 12 we had earlier here. And so another thing I would like to display is the expected value. And then click on compute. And then you have the results that I have pasted here. Okay? And you notice that you have the chi-square value and the p-value. Our main interest is the p-value for drawing our conclusion. Before we do that, let us also see how to use the chi-square calculator to compute the p-value by hand. That is, this p-value, where is it from? We can use the chi-square calculator. Go to statistics, go to calculators, go to chi-square calculator, supply the degree of freedom. The degree of freedom is how many subgroups do we have? We have 1, 2, 3, 4, 5. 5 minus 1 is 4. You must always say 5 minus 4 minus 1, and then you have what? Your 4. Then we want to look at the upper tail. The upper tail of what chi-square test value? The test statistic value that we got was 36 over 12, which is 3. So I'm going to put 3. Make sure that this is what? Greater than or equal to 3. You wouldn't really have to do this because you're using what? StatCrunch. But I wanted us to see where this p-value came from. And that is 0.5578254, which I've provided the picture here. So with that said, we can go back to our table to draw our conclusion. So looking at the conclusion here, you recall that because the p-value in this case, what was our p-value? Our p-value was 0.5578 compared to our level of significance of the test, which is alpha, that is 5%. So this is 0.05. What is the relationship? The p-value is far exceeding the alpha, so we fail to reject the null hypothesis in favor of the alternative. Remember, the alternative hypothesis is the research hypothesis. So this means that since we're going with the null hypothesis, that means we do not have sufficient evidence in the sample data analyzed in the sample data to state that the alternative is true, to state that the absent days occur with unequal frequencies. Emphasis on the do not have, that absent days occur with unequal what? Frequencies. So that means that the status quo remains. That is, this data only aligns closely with the fact that they occur with the hypothesis that they occur with equal frequencies during a 5-day work week, despite the slight departures. So, with that, we have come to the conclusion of that question. So, let us consider next a scenario that the chi-square goodness of fit would not be appropriate for. So, you have quality control. A company advertises that its premium mixture of nuts contains 10% Brazil nuts, 20% cashews, 20% almonds, 10% hazelnuts, and then the rest are peanuts. You buy a large can and separate the various kinds of nuts. Upon weighing them, you find that there are 112 grams of Brazil nuts, 183 grams of cashews, 207 grams as almonds, 71 grams as hazelnuts, and 446 grams of peanuts. You wonder whether your mix is significantly different from what the company advertises. Question A. Explain why the chi-square goodness of fit is not an appropriate way to find out. You see, because weights, remember you weighed, so because weights are quantitative continuous measures, they're quantitative continuous measures, the chi-square goodness of fit is not an appropriate inferential statistical technique to use. In other words, once you have to measure, you're not going to use this. There are other methods to use. Otherwise, part B answers, what might you do instead of weighing the nuts to use a chi-square test? That is, you really want to use the chi-square test. The requirement for using the chi-square test is that we must have quantitative discrete data in the form of count data. This was emphasized at the beginning of this video. So we should instead count the number of each type of nut while assuming that the company's percentages are based on counts rather than weights. And that, unfortunately, is not clear in this case. So this will represent a scenario that does not fit a scenario whose question can be answered using the chi-square distribution or chi-square goodness of fit, and then there might be a need to revisit the design process for the whole experiment. In the next video, we'll see more examples on other applications of the chi-square goodness of fit test and the chi-square independence test or test of homogeneity.